My dear student, Assalamu alaikum. This is your Iqbal sir. This is my second video on periodic motion. Okay, in this video we will discuss about some mathematical formula regarding simple harmonic motion. Linear simple harmonic motion. When the force acting on a particle is directly proportional to the displacement. When the net force acting on a particle is directly proportional to the displacement and opposite in direction, the motion is said to be linear simple harmonic motion. Here the net force, that is F, net force directly proportional to the displacement x, directly proportional to displacement x. Okay, here the net force F and displacement x acting opposite in direction. That's why here we used a negative sign. Negative sign come here due to the net force F and displacement x acting in opposite direction. And when we remove proportional symbol, we put a constant which is k. Okay, and this k is a constant of proportionality, and which is called force constant of a spring. K is the force constant of a spring. Now the differential equation of motion. Differential equation of motion is m into d square x by dt square plus kx equal to 0. Here m is the mass and this is the differential term, and k is the force constant, that is force constant of a spring, and x is the displacement. Now we divide this equation by m, we get this equation. In this position, when you divide this equation by m, in this position k by m we put omega square, because we know that the force constant k equal to m omega square. From this equation you can write omega equal to root over k by m, root over k by m. The solution of this differential equation is x equal to a sine omega t plus phi. Here x is the displacement and a is the amplitude, and this is this term, that is omega t plus phi. Omega t plus phi is called phase. Omega t plus phi is called phase, and phi is called epoch of simple harmonic motion. Here phi is the epoch. Epoch means time. Here epoch indicates time. Okay. Now, so the equation of simple harmonic motion is x equal to a sine omega t plus phi, and this is the expression for displacement. Now the expression for the velocity will be like that. We know that velocity v equal to dx by dt, that is the rate of change of displacement. We know that velocity v equal to rate of change of displacement, that is dx by dt. Now in this position of x we put the value and differentiating this term with respect to time, we will get a omega cos omega t plus phi. From this equation you can write v equal to omega root over a square minus x square, b equal to omega root over a square minus x square. Here the velocity is 0 at extreme position. Velocity is 0 where? At extreme position, and maximum at equilibrium position, and maximum at equilibrium position. Now this is the expression for periodic time of simple harmonic motion. What is the periodic time of simple harmonic motion? The period of simple harmonic motion is defined as the time taken by the oscillator to perform one complete oscillation. This is the period of simple harmonic motion is defined as the time taken by the oscillator to perform one complete oscillation, and every time t, after every time t, the particle will have the same position, velocity and the direction. Same position, velocity and direction. And the expression for time period is equal to twice phi by omega. Okay, from this equation we can write by putting the value of omega from previous slide, that is omega equal to root over k by m. Putting this value into this position, we get t equal to twice by root over m by k. From this equation we can write that t proportional to m, t proportional to m, t proportional to m when nk constant, and t proportional to root over 1 by k, t proportional to root over 1 by k. Okay, when n m is constant. Frequency, this is the expression for the frequency. What is the frequency? The frequency represents the number of oscillations. The frequency represents the number of oscillations that the particle undergoes per unit time interval. The frequency represents the number of oscillations that the particle undergoes per unit time interval. Here frequency is the inverse of period. The inverse of the period is called the frequency, that is f equal to 1 by t. By putting the value of t, we get omega by twice phi, that is f equal to 1 by twice phi root over k by m. Here in this position, if we put the value of omega equal to root over k by m, then we will get f equal to 1 by twice phi root over k by m. This is the expression for the frequency of simple harmonic motion, and the units are cycles per second. Units of frequency are cycles per second, which also can be write as a hertz, H-E-R-T-Z, hertz, and which is denoted by Hz. Now the time period and frequency can be write like that, we get from this equation. Okay, here from these two equations we see that the frequency and time period depend only on mass of the particle and force constant of the spring. Mass and force constant and mass, that is the time period and frequency depends on mass and force constant. They do not depend on the parameters of the motion like amplitude of the oscillation. It doesn't depend on amplitude, Here the frequency is larger for steeper spring, large values of k. Here the frequency is larger for steeper spring, that is large value of k, and decrease with increasing mass of the particle, decreases with increasing mass of particle. From this equation we see that the frequency f is proportional to the spring constant. That is, if the value of k is large, then frequency will be large, and if the mass of the particle is increases, the value of frequency will be decreases, because here the frequency and m are inversely proportional. Frequency f and mass m are inversely proportional. That's why if m increases, f will be decrease, but if m decreases, f will be increase. Okay, that's for today. No more today, more when we meet in again. Till then, Allah Hafiz.